Okay, so let me just start by recapping what we did yesterday. So the idea is that we have a diffusing particle, which I'll indicate by that, which has a resetting process to a resetting position, let's call it XR. And there's an absorbing target at xt. And in the problem I was studying yesterday, for simplicity, we took the target to be at the origin and the resetting position to be the same as the initial position. In principle, they could be different. And the main result that we derived was the survival probability for this diffusing particle, probability that it hasn't been absorbed up to time t. And we derive the Laplace transform of that, which I'll denote. So that's the Laplace variable, and x naught here because xr is equal to x naught. So I'll just call the initial and resetting position x naught. And the expression that we got was the following. And that was, in my labeling scheme, equation 12. And alpha here is r plus s over d to the half. And an immediate corollary of that is that we get by setting s equals to 0, we get the mean time to absorption. So we'll call that t, and this was one of the equations I forgot to label. So generally, t is the Laplace transform of the survival probability with Laplace variable s set equal to 0. So that was actually equation 8. And so putting s equals 0 in here, I get e to the alpha naught x naught minus 1 over r. And alpha naught is r over d to the half. And what we discussed last time is that this has a unique minimum as a function of r. It diverges when r goes to 0 as 1 over r. And it diverges when r goes to infinity as e to the r to the half. And in between, we've got some minimum at, let's say, r star. And what I want to do just now is to analyze the position of that minimum, because that gives in some sense, it optimizes the time to absorption. If you're thinking of a search process, this particular value of resetting, gives you the minimum expected time to find your target. So just a simple matter, we've got this expression for t. Oh, by the way, yeah, forgot to label it again. This was 13, this equation here. So if I use 13 and compute dt by dr, simple matter of computing the derivative. I won't give the algebraic details, but if I set this equal to 0, then the equation I get actually takes the form of a transcendental equation for a variable y, which is alpha naught x naught. Now this equation has a unique solution for y greater than 0. I mean, it's got a solution for y equals 0. That's kind of not relevant. And we're looking for one for y greater than 0. So you can see that, well, it's going to be a unique solution. Because if that's y over 2, and this is how does it go? 1 minus e to the minus y. Okay, there's a unique intersection, so a unique solution. And that value, y star, okay, you can calculate it numerically. And it takes the value, I don't seem to have written it down here. Oh, yes, I have 1.5936, and so on. So we want to put a physical interpretation on this. So, by the way, yeah, I said I've minimized with respect to r, and of course r is wound up in the variable y, because r appears there. So what does this variable y mean? Well, it's x naught, and then I can think of alpha naught. I can write it as d 1 over, all right, alpha naught is 1 over d over r to the half. So it's the ratio of two lengths. The first length, x naught, is simply targeted at the origin. We're resetting to x naught. So it's the distance of the target from our resetting position, where we thought the target should be. So it's distance to target. And then if we think about d over r to the half, that is a length. It's got dimensions of length. If you think about it, it's the typical distance diffused between resets. So 1 over r is the typical time between resets. And so d over r gives the distance diffused between resets. So it's a typical distance. And so it turns out that the optimal ratio is about 1.6, okay, which is fine. And that makes sense, because then we understand that, yeah, if the distance diffused between resets is very small, that's when we're out here, then this goes to infinity. And if we're down here when r goes to 0, yeah, okay, never mind. Let's just leave it at this interpretation. So if we optimize this, the ratio is about 1.6. So what I want to do now is, we've looked at the mean time to absorption. Let's look at this survival probability. So here, it's wrapped up in the Laplace transform. So to get it into the time domain, I need to invert the Laplace transform. So this is still section 1, 1f. We're going to have a look at the survival probability. For this problem of diffusion with resetting and absorption. So the inversion, remember we had a little look at inversion of Laplace transforms last time. So what we would like to do is to calculate the Bromwich inversion. And, okay, it's integral with respect to s, e to the plus st. And then it's the q tilde. So let me just write it out. 1 minus e to the minus alpha x naught over s plus r e to the minus alpha x naught. And remember, the way that we should do this is that we need to take gamma to the right of any singularities in the complex S-plane. So we need to check out the singularity structure of this function here. And what we see is that, well, we've got an alpha, and that's a square root. So there's actually a branch point at S equals minus R. Now, in addition, this denominator is going to give us a pole at some value of S at which this is equal to 0. So we've got two singularities in the complex plane. So if I sketch, this is the complex S-plane. So that's my Bromwich contour. It's going from gamma minus I infinity to gamma plus I infinity. Then we've got a pole sitting here, so I'll mark it with a cross, at minus R. And then, no, I beg your pardon, minus S naught, which is the value of S at which that's 0. And then we've got at minus R a branch point, so we'll put in a branch cut there. Sorry, I'm going to call that S naught, but it's negative. And this is S equals 0. So when T is large, it's this pole that will dominate the survival probability. And this branch point here and the branch cut will give a correction. So let me just focus on the dominant term, which comes from the pole. So we've got a pole at S naught equals minus R E, and it's minus X naught over R plus S over D to the half. So I need to solve that equation, which is a bit nasty. But you'll notice that if X naught R to the half over D to the half, which is actually this variable Y here, if that is large, then S naught is going to be small, so it's a very good approximation. This is at minus R e to the minus Y. And for S naught small, this requires Y to be large. Right? And the correction is going to be very small if I put that, if I iterate to try and get this, if I put it back in there, it's not going to make too much difference. Okay? So then, the contribution from the pole, so the pole will give the dominant contribution to this integral. And what I get, so remember, the pole is just calculus of residues. Essentially, to get the residue, I cover that up and then put S equals S naught upstairs. So I will get Q, the dominant term, will be e to the S naught t from here. And remember, S naught is negative, so this is a decaying exponential. Then this stuff here, well, that's actually not going to do much, but let's just write it out. Anyway, it's e to the minus r plus S naught over d to the half x. So if y is large, then S0 is approximately this. And effectively, if y is large, that's e to the minus y, and we can forget that. So to leading order, so I'm just being a physicist here, and we just calculate things to leading order, it's simply this. Our survival probability will be, remember S0 is approximately this, so I get e to the minus RT e to the minus y. So this expression, for those of you, I don't know, maybe you've come across this, an exponential of an exponential, or a negative exponential of an exponential. This is something typical of extreme value statistics. And usually this appears as what's called a Gumbel distribution. And I'll just make an aside on explaining what a Gumbel distribution is. And then I want to show why, in fact, we should expect this form for the answer. So briefly, let me, as I said, so I'll just say this is Gumbel form. So let me make an aside on a Gumbel distribution. The idea is that we want to consider the extreme values of a bunch of random variables. So let's say we have n are identically distributed, independent identically distributed random variables. We want to know information about the maximum of that. And the simplest way to do it is to look at the cumulative distribution and look at the probability that they're all less, all these random variables are all less than some value. So if I have n IIR dv, and let's say they're PDF, I'll just call f of x. And so I'll denote PNM is the probability that they're all less than m. So this is the probability that the max of these n random variables is less than m. Well, each of the random variables must be less than m. So the probability is integral from, okay, let's assume it's an infinite domain. Right? That's because they're independent. Okay? Now, I can write that as exponential n. Then it will be just taking the log and doing the exponential. Then I can write this, in fact, as 1, assuming f is normalized, 1 minus integral from m to infinity. And we expect this to be small, this bit here, right? With the probability that one of them is bigger than m. So let's assume that m is large enough that this is small. So then we can expand. And then the question is, what is the form of this depending on the different possible forms of f? Now, typically, we're looking at the extremes of the distribution. So you might expect f to decay exponentially with x. So let's assume it's exponential decay. So if f of x goes like a and little a here are constants, then in fact this probability here will approximately be exponential, expanding the log and doing the integral. I get minus n a over a e to the minus am. And you see, that's the Gumbel distribution, and that's the Gumbel form. And that's precisely the same kind of thing that we've got here. Right, so that in the Gaussian, it shouldn't make much difference. The difference comes if you take it a Powerlaw, if you have a long tail, something that's, if it's decaying exponential or faster, you'll get Gumbel. Whereas if it's slower, Fréchet, you get something called Fréchet distribution. I think, yeah. So that's there's only a few classes of the distribution for extreme values. And the Gumbel is the usual one. Okay. Yeah. So why should this Gumbel thing appear? That's the question. We want to understand that. And actually, if you think about it, okay, it's quite natural. So again, I'll just give a brief explanation of why we see the Gumbel distribution. Yeah, so that was an aside. And now we're back to this. And the idea is that if we think of the trajectory of the resetting particle, okay, the target here is over here. And then the resetting and initial position are here. So for it to survive, remember, it resets and then it does this. We can think of the trajectory to be a sequence of excursions, and then it resets. And these are independent, so this is because the resetting process is Poisson. And so what we're asking basically for the particle to survive, then it must survive in each of these excursions, right? And they're independent. So that's when, so if you like, the furthest it got to the left in any of the excursions must be less than a certain value. And then if you think about that, that just is an extreme value statistic. Okay, we've got a number of independent excursions. So we have, if you think about it, it's resetting with rate r. So in time t, there'll be rt plus some correction of order rt to the half, independent. Excursions. So we can say what we need is that the max in the excursion, the max displacement to the left should be less than, okay, if xt is at the origin, it's got to be less than x naught. So our survival probability is that probability to the power RT. Okay, this is an approximation, but the corrections will be quite small. But then we have to be a little bit careful with this. So we want the survival probability of a diffusive particle. And that we know. Remember last time we derived that? It looked something like an error function. But we have to be a little bit careful because we have to average over the duration of the excursion. So in here, we need to average from 0 to infinity, dt. Then yeah, we'll have r e to the minus rt. That's the distribution for the length of the excursion. And then the survival probability in the excursion is what I called QD last time. So this is the distribution of the duration of excursion. And this is an error function that we saw last time. And then, okay, the magic is, if we do, well, actually it's not magic. Remember, we've used this identity last time that, in fact, this is almost like the Laplace transform of this. And we derived last time the expression for the Laplace transform of the survival probability for a diffusive particle. And this comes out as something simple. And in fact, we get 1 minus e to the minus x naught r over d to the half to the power rt. So this is an approximation, but you know it's reasonably well controlled. And that gives us, that coincides with the exact asymptotic that we, okay, when we take the log and exponentiate, I get exponential RT, and then I expand this, I get minus e to the minus x naught r over d to the half. And that coincides with the exact asymptotic we derived here. So that's why we get a Gumbel type distribution, because basically we have to have the survival of order RT independent excursions. Okay, good. So what I want to move on to now. Yeah. I hear what you're saying. It should be somewhere. So usually in these dynamical problems, yes, there's some eigenvalue involved. So I'm not sure of what, though. Okay, I'd have to think about that. Yeah, it must be, because usually that's what you get, that, yeah. You have a discrete eigenvalue and then some spectrum, and this will be the leading discrete eigenvalue. Yeah, I'd have to think about that. It's a good question.
Maybe just
I believe so, yeah. There shouldn't. Effectively, we've probably done it along the way. Yeah, there should be a quasi-stationary distribution. So that just means, just for those of you not aware, so that simply means if you condition on surviving, then usually there is a quasi-stationary state that appears. And I believe that will be the case here. We haven't actually done that. But that's a good question. Okay, so what I want to move on to now, so I'll just continue on this board, is so far we just considered one diffusive particle and a target. And a natural question is, what happens if you have a bunch of searches, you know, like a team of people searching for a target? And this problem has been studied for the case of diffusive particles. And the idea is, so this now is section 2. So the idea is that we have many So by searches, I just mean my particle. That generally has some diffusive dynamics. And let's try and be general. There may or may not be resetting. There might be some other dynamics. But we just think of each particle as a searcher. And so we've got a whole team of particles. So in our case, when we've got resetting, let's say that their initial position and the resetting position are the same. So they start and they reset. And each one has its own position. So it's kind of like, I remember when I was young, you see teams of policemen searching for evidence, you know, and they'd be in a line and each one would be searching. And they would each have their own position, really, in the line to search for evidence. So xi is the position of one of the searchers, and I, let's say that there's n of them, so I goes from 1 to n. So what we're thinking of is that we've got our target, let's say, is at the origin. Then there's n of these guys are distributed uniformly, so they end up, okay, like this. And these positions here, these are meant to be the positions of the xi. These are all random variables. So we have to be a little bit careful about how we set this up. And the easiest way is if we put a window here and say we're considering, okay, so the target's at the origin. We're considering a region going from L over 2 to minus L over 2. And we're going to scatter the initial positions of these searchers in that window. And then we will take the limit of L goes to infinity and the number of searchers going to infinity. So we'll take the probability distribution for xi. Okay, so pxi, dxi. So they're uniformly distributed. And rho will be n over L is the density of searchers. And we're going to take the limit n goes to infinity and L goes to infinity. Okay, but first of all, now let's think about, okay, the survival probability. And now we're going to change from, before we thought of the survival probability of the particle. In this case, when there's a whole bunch of them, it's more natural to think of the survival probability of the target, right? Because the target just takes one particle to hit the target, and then it's over for the target. So now we just change and say it's the survival probability of the target. So let me call this capital Q. And it's a function of time, and it's going to depend on the collection of positions of these guys, the initial positions of the searchers. But if we think about it, for the target to have survived, then none of the searchers have touched it. So in fact, it's the product of the survival probabilities of the individual searchers. No, the target is not moving. The target is fixed. A moving target turns out to be a more difficult problem. Okay, I'm not going to address that here. It's a relevant but simply more difficult problem. What I will consider hopefully next lecture is when we don't know when the target is. So it's fixed, but itself has a probability distribution. So that's... Well, it's like so the idea is whenever a searcher touches the target dies. So that's what I mean by the survival of the target. That no searcher has found it yet, but it's fixed. Okay. And so what we need to do is somehow to average over the xi. Now this can be a little bit tricky. So there's a subtlety here that, remember, these survival probabilities we're going to be interested in a long time. And so these can be very small quantities. that, for example, could depend exponentially on time. And there you have to be careful about what an average means. So I just want to just give a simple example where you can be deceived. And I want to introduce the, it's the physics terminology, and so it's in the literature. So I just mention it. Often we talk about quenched and annealed averages. So what do we mean by that? These are just physics words, jargon, it doesn't matter where they come from. Now the point is that, let me just take a simple example. If I have a random variable, let's say x, so let's say it takes two values, e to the an with probability 1 minus p, and e to the bn with probability p. And I want n to be large. And let's say p also itself is small, but depends exponentially on n. Now, if I take, so clearly, so n is large, so this is very small. So the typical x is clearly this one, right? With overwhelmingly large probability, x will be e to the an. However, if I take the average, so okay, if I take the expectation of x, I'm going to get e to the an, 1 minus e to the minus cn, plus e to the b minus cn. And the interesting thing is that, so it's either this term, e to the an, or this term that will dominate. And it can be that this can dominate. So this will be, the leading term will be e to the b minus cn if somehow b minus c is greater than a. So in that case, the average gives something very different from the typical value. And it's because we're dealing with these exponentials when n is large. So something here, basically, something with a very small probability, minus c to the n, because b was large, in fact, dominated the average. So a very rare event dominated the average and gave us a sort of skewed answer. And this is called the sort of just the straight average like that is what's sometimes referred to as the annealed average. And what we really want is the typical value. So if I take the expectation of log x, well then, okay, things work all right. So I've got, it's an with probability 1 minus e to the minus cn plus bn e to the minus cn, and this is clearly going to be equal to an. And so the exponential of the average of log x gives the typical value. And that's what is referred to as the quenched average. Right, so all it means is that we take the average of the log and then exponentiate it. So we have to be a little bit careful in this problem to distinguish when we do the average of this, just the straight average, which is what I call annealed average, and a more reliable estimate of the typical behavior, which is the quenched average, and we have to check whether these two things are the same or not. Okay, let me clean the boards there, and we'll go on with that program in the second half of the lecture. Okay, so feel free to chat. Right. So just to recap, we're now thinking about many searches. And we're thinking about the survival of the target. So we've got this bunch of searches, and then there's the target here. So take it 0. And Q, the survival of the target. For the target to have survived, then basically it hasn't been touched by any of the searches. So if we think of the individual searches, then each of them has to survive. So it's the survival probability for individual searches that we've already calculated. So first of all, let's calculate what I called the annealed average, which is just the direct average of this. Right, so we'll have the average of Q. Then each of these are independent. So in fact, this becomes the average of Q to the power n. Which I can write as exponential n log Q. Now the trick here is that we're going to be thinking about large times when, at large times Q is going to go to 0. So, oh, by the way, I'm using here the angle brackets are my average over the positions xi. And here the angle bracket means the average over xi. Okay, so angle bracket is average. So what have we got? Exponential n. Then I want to write it as log. The trick is to write it as 1 minus 1 minus q. And I can put the average over x there. Now, yeah. Okay. So the average of q remember, I'm assuming that I've got this window of size L, and the position is uniform in the window. I'm sorry? Yeah, so the initial position is the same as the resetting position. Okay, I've made that just to simplify things. So each searcher has its own initial position, xi. But each one is independent, so I'm just taking for each one I take the average over its initial position, and that will be the same, the average will be the same for all of the searches. Okay, so this is the initial position. Sorry, if you want me, I can put the xi in there. So 1 over L integral minus L over 2 to L over 2 dx. Yeah, and then I write it like this: 1 minus q. So the first term just gives me 1, of course. And then I have minus 1 over L Now, the point is when x becomes very large, so the initial position is very far away from the target, then the survival probability goes to 1. So actually, this integral, I can take the limits L goes to infinity, and it will converge to some finite value. And so this term here will, in fact, be 1 over, of order 1 over L. Okay? So this integral, the point is, that's why I've written it that, it's of order 1, so it's some finite constant. And then this allows me then to expand here, what I'll call Q average, which is just this. If I expand that, I get exponential okay, yeah, n log 1. Then let me write this. It's symmetric, so I can write this as minus 2 over L, integral from 0 to L over 2, dx 1 minus q. Sorry, didn't write that very well. I'm writing it usually as t given x. So now I expand the log, and I have an n over L, and then I can take n goes to infinity and L goes to infinity. It becomes exponential minus 2. I get the n over L is rho, and then I have this integral, which I'll call I1 of t, which is this integral here, 1 over L from 0 to infinity of that. Okay, so let me just write that up. Okay, sorry, that's actually quite simple. I made hard work of that. But what I've got is that the Q average takes this form. So all I need to do is to evaluate this integral, which will depend on I. And this is actually quite general. Okay, so I haven't, all I've said is the initial positions of these things. It doesn't actually matter whether they're resetting or not, like, or what exact stochastic process they follow. Okay, then the second average is the quenched average. Remember, then I want to average log. And remember, the quenched average gives me the typical value, or should give me the typical value of Q through and then this will be exponential the average log Q. If I take the log of this, I'm going to get a sum of terms. So when I average, I'll have n average log Q with respect to x, which will become exponential minus 2 rho. This is in the limit n and L goes to infinity. I'll get exponential minus 2 rho, and then I2 of t, and I2 will simply be minus, if I've got my minuses right, integral from 0 to infinity dx of log Q. Okay? Yeah. There's nothing, sorry, it's turning out to be a little bit heavier than I thought to write this on the board. It's actually quite simple. Okay, all I'm doing is taking the log of this and averaging. And that's what I get. So for any problem to calculate the typical and average values, I've got these two integrals, I1 and I2, to compute. So first of all, let me consider a well-studied problem where the searchers are just diffusing particles, so no resetting. Let's consider the limit of no resetting. So that was all the first part of 2. That should have been 2a. So now 2b. Let's consider the case of diffusive searchers. So there's no resetting. So we know from last time that for a diffusive particle, the survival probability Q is given by this error function. So this was equation 6 from last time. And so, okay, if we simply put this in this expression here, it turns out, and I won't go into the okay, so I1, if I change variables from x to u, which is this variable here, I'll end up with 2 root dt, integral from 0 to infinity du, error function of u. Okay? I'll just leave that as an exercise, just to change a variable. Then here there's a nice thing happens is that you can actually do this integral. And it takes a simple form. I'll leave that as an exercise. So it comes out as 2 root dt over pi. On the other hand, I2, which is this, where's it gone? This integral here, Again, let's change, Q is the same thing. We change variables from X to U. So I2 will be minus 2 root dt. No, sorry, I'm losing it here. Okay, it will be I2, okay, is this. So it's going to be integral of log yeah. Something's not con. Yeah, so here, I beg your pardon, this should be the complementary error function, because that was 1 minus q. And here I should have log of the error function. But it actually doesn't matter too much. Okay, so this is nice because the integral of the complementary error function, we can do that integral. This integral we don't know how to do, but it doesn't matter. It's just some number that that is finite. And the important thing in both cases is that you have this scaling here. You have a root dt. So in both cases, so the survival of the target, both in the average and the typical case, will go like exponential with some constant that depends on whether we're looking at the average or the typical case, but it will be rho root dt. So to physicists, this was an interesting result because you get a stretched exponential relaxation. And generally that's considered a slow relaxation time. A normal relaxation, you would say, is something that decays exponentially. And here, it's a stretched exponential. And okay, so that suggests some spectrum of relaxation times. So it becomes, that's an interesting structure for this distribution. And what we want to see is how that changes when we put in the resetting. So now let's do it again, this time, with resetting. Okay, so just to stress again, this is a slow, stretched exponential decay. Right. So in the case of resetting, we've got an explicit expression for the Laplace transform of Q. So we need to try and take advantage of that. So if we go back to computing the integral I1, so this here, let's take the Laplace transform of this integral, because then it gives things in terms of the Laplace transform of Q, which we have an exact expression for. So if I define I1 tilde, then from the first term, I'm going to get a 1 over s. Okay, so I get the integral with respect to x. And then I have a 1 over s minus q tilde. And right, remember, I have my exact expression for q tilde that okay, we saw earlier. So if I simply substitute that in, I get, okay, and I'll leave you to fill in the gaps in the algebra. I get s plus r e to the minus alpha x over s plus r e to the minus alpha x. Then it turns out that's nice because we can actually do, this is an elementary integral that one can do. Right, you just do by inspection. And I get r plus s over s r alpha log of s plus r over s. Right? So this is an exact expression for the Laplace transform of what we want. Then, as usual, from the Laplace transform, we can extract the long-time asymptotics by looking at the small s behavior. So this is, sorry, let's remind ourselves, this is exact. Then we look at the small s behavior to get the asymptotic. And the leading small s behavior is actually going to come from 1 over s and then the log s here. So it's so I'm going to get minus the 1 over s, I've got a minus 1 over alpha, 1 over s log s. Oh yeah, sorry, and alpha itself contains s, so when I'm expanding it becomes alpha naught. Okay, so that's the leading small s behavior. And this is actually a little bit difficult to invert, so we have to think about this a little bit. And the way it works is we notice that if we take the Laplace transform of a log, it's a bit nasty. And what happens when we change variables to u, you end up with 1 over s. Okay, that's simply just changing variables. And, okay, so if I look at this, this actually, the log s here, then I can do the exponential integral. And the log u gives me an integral e to the minus u log u. And that integral is actually Euler's constant, or minus Euler's constant. So that's from the u bit here, and then I get minus, from this I get minus log s over s, where here, this is Euler's constant, and I'm writing it in this form, an integral representation. Okay, so why am I telling you that? So then this then shows me how to invert log s over s that appears in here, and allows me to extract the long time behavior. So what I learned is that the inverse Laplace transform of minus log s over s, okay, is going to be log t, and then the inverse of this, which gives me log t plus Euler's constant. So finally, I get the leading time behavior, excuse me, that should be the tilde, of I1 of t is going to be, put everything together, okay, that's just inverting this, using this formula here. So this I, in fact, goes as log time plus constant. And so if I put this is the important bit, if I put this into the Q average, then it will be, the leading behavior will be some constant that I haven't I haven't computed, but it doesn't matter. But what we're interested in is what goes on inside the exponential. So remember, it's here. So Q average is exponential minus T rho I1. So if I put that in, I've got minus 2 rho D over R to the half log T. And then, of course, exponential of a log is T to the minus 2 rho D over R to the half. And so this is a power law decay. And that's interesting because that's very different from here. And this was a slow decay because it was stretched exponential. And now here we have a power law decay, which is even slower, if you like. So we have to be a little bit careful because remember, there's the two different averages, the quenched and the annealed. And we need to check like what the quenched average gives to see whether it gives something similar. But let me first of all just make a comment on this. The exponent is, okay, the power here is basically D over R to the half. So we met that length before. So it's 2. So it's 2 times the diffusive distance between resets. Over, so 1 over rho. And 1 over rho is basically the distance between the searches. So again, this exponent that comes in is a ratio of 2 lengths. So if the distance between searches is large, much larger than this diffusive distance, then this exponent becomes small and you have a very slow decay of the survival of the target. So basically the target will survive a long time. Okay, so but let me get on to now I2, the quenched average. So here, oh, we've got a bit of time. The I2 is the integral from 0 to infinity, dx, then log q of t given x. And we're going to be interested in large T. So remember that earlier we computed the large time behavior of this Q. So for T very much greater than 1, Q was actually equal to e to the, what was it again? Minus RT excuse me. It was e to the s naught t. Because remember that came from the pole in the Laplace transform of Q. And here we need to keep in the expression for s naught. Remember, S naught was given by minus R e to the minus R plus S naught over D to the half times X naught. That's good. So then if we simply put this in here, I2 will become, so again, this is for large T. We're going to have a minus T, integral from 0 to infinity, the X naught, S X naught. Then it turns out that you can actually, this integral here, even though this looks quite nasty, you can do this integral exactly. Okay, so we were quite pleased when we did this. And, okay, we've got a bit of time if we want to sort of spend the last 20 minutes doing an integral. Maybe not. Maybe I'll finish up a little bit early. But the way to do it is, okay, if I substitute U equals minus S naught over R, I end up with U equals, in this exponential, if I, remember, I've got the y, which is X naught R d to the half. And then I'm going to have, if I pull out the R d to the half, I'll have S naught over R. So I end up with 1 minus U to the half. Okay, where Y is alpha naught X naught. And alpha naught is R over D to the half. So if I invert this, I get Y equals minus log U over 1 minus U to the half. Then, basically, if I change variables to Y, at I2, okay, this will become integral from 0 to infinity dy uy. And in fact, that integral, okay, I don't know how interesting it is to actually to drag you through it, but there's an integral that you can do. And let me just give the answer. dr to the half, it's 4, 1 minus log 2. So anyway, that's the result after doing this intro. So you look a bit puzzled. No. The time, yeah, good. It's there. And it fell off. Yes, thank you. Yeah, this was meant to be I2 over T. Okay, so I2 is this constant times that. So just to summarize, the average survival probability goes like, so here this is kind of a lazy physicist symbol, which means that we're not caring about the prefactor. We're just interested in the time dependence. So that means there is some constant there. Let me just write it as some constant t to minus 2 rho d over r to the half. Whereas the typical survival probability goes as, and okay, yeah, here again I've not kept track of the constant, but the important thing is that I've got exponential from this minus, all this stuff becomes minus 8 rho 1 minus log 2 dr to the half. Then the important thing is t. So the average value decays very slowly with time, but the typical value decays exponentially, so quickly with time. And that's actually, you know, if we're really interested in as a search strategy, having a team of searchers, then we want something that decays. This is the survival probability of the target, remember, so we want that to decay quickly with time. And that's typically what happens. But somehow the average is very, very slow. So here, the quenched and annealed averages are very different. And usually that, as in the example I gave, the trivial example, is because of some rare realizations that dominate the average. And here, basically, the explanation is that the average is dominated by very rare initial conditions where, by chance, so remember we've got this picture here, we distributed our searches on a window, and you could have some, by chance, you could have distributed them all very far away from the target. So right at the beginning, there's a small chance of these things being nowhere near the target. Then because of resetting, this initial condition is remembered. And so it's these events that actually would give a long survival time to the target. And at large times, these events, although they have very small probability, they dominate the survival probability and make it decay, on average, slowly. Whereas typically, you'll get typically you'll get the searches distributed evenly, then the target, there'll be a searcher near the target, and the target survival will decay exponentially. So that's the idea. The average is dominated by rare initial conditions where the searchers are far from the target. And we have a very strong memory of the initial conditions. And that comes through resetting. And then finally, the important thing is that the typical survival probability decays exponentially. And so, again, this is very different from purely diffusive searches where it decays as a stretched exponential. So the survival of the target decays much more quickly, which is what you would want in a search process. So the typical Q decays faster than purely diffusive. Okay. Yeah. Okay, I think I'll just finish up there.